Hello, my approach 2 friends. So, if you're doing approach 2, your code works like this. You start with a fringe. Your data structures are a fringe, which is a priority queue, and best, which is whatever you decided it to be. It is going to store our best known distances and our parents. So we start by adding the source to the fringe only with some arbitrary priority. It doesn't actually matter. And then we initialize best and at whatever way seems appropriate. We run the algorithm as follows. We take the closest vertex in the fringe, like the thing we think is best from the fringe, and we'll call that vertex v. If v is the goal, so as closest is just minimum priority. If v is the goal, we're done. For every edge from v to w, we relax that edge. So in other words, for all the neighbors of v, we'll call them w, we do the following computation. If the distance that we have from the source to the vertex v, that is along the whole path, whatever it may be, this is stored in best, plus the Euclidean distance from v to w, that's the edge weight from v to w, if that sum is less than what we currently know is our best distance to w from the source, which presumably should start off as infinity, or if you want, you can do something slightly different where you say if it's not in there, then it's infinity. Whatever, however you want to do it. If it's less than the best thing we have so far, then what we do is we update best so that the new distance is equal to that calculation we just did, right? This is the new best. We also need to add w to the fringe with the priority equal to the distance to w, which is the sum we just have so far, plus, because it's a star, we also include h of w, which is the estimate of the distance from w to the goal. That's the heart of a star. If you omit that, it's Dijkstra's. With this, it is now the fringe. Okay. Now, one issue here is you'll end up with multiple copies of w on the fringe, and that's actually totally okay. It turns out that you can pass the autograder tests, including the 3x autograder test, if you code everything just like we did, I guess, even if you don't have any kind of marked data structure. The code as it shows here can pass the 3x autograder test, but if you find yours is too slow, you can also add a marked data structure as shown on the next slide. Okay. Now this is approach 2x. It's a little faster. It's very similar to what we just did. It's just that now we have an additional data structure called marked. Now you shouldn't need a marked set to pass the timing test. Now I know my face is covering this up, but you can look at the slide. This says to pass the timing tests. Okay, sorry, my head's in the way, but oops. So what this approach does is you start by adding the source to the fringe and you initialize best, and I guess you should also initialize marked, but I'm assuming it's all empty, right? So hey. We dequeue the closest vertex on the fringe, which we'll call v. If v was already marked, we'll return. We'll say this is something that was already visited, so there's no need to do anything. If v is the goal, we're done. And then at this point, if we've dequeued v and there's still more work to do, we'll note that v has been marked. We're just saying to the world, v has been handled, so if it comes up again, don't do it. And then we'll say, for each edge from v to w, we'll relax the edge, just as I said before. And everything here is exactly as before. Okay. Now this will still result in multiple copies of w on the fringe, each with different priorities, and that's still okay. It'll just now be fewer of them because there are going to be some things that we avoid exploring, right? So that is, there are some nodes that whenever we dequeue them, now we'll have a return if we marked, so it'll speed things up a little, but honestly, it's not going to be that big of a difference, okay? Now, a warning, if you mark a vertex when it is added to the fringe, that is, instead of doing add v to the mark set after dequeue, if you instead do it here, add w to the fringe, mark w, your code will fail. And the reason is that we're no longer doing the approach that we discussed in class. So you can actually take approach 2, the simpler version, and show that it's basically exactly the same thing as approach 1. You can do the same thing with 2x, but once you change this mark over here, you'll find that it's a different approach. There's like a very subtle little point. And if you take 188, you'll learn more about it. Okay. So, I mean, it's kind of interesting. I don't know if it's that deep, but you just can't mark down here. The proof of a star's correctness no longer works. Yeah, not the most exciting thing. Okay. So again, there's not really any particular, I think with this one, there's not really a gotcha that's any different from the rest. I mean, go back to the common bugs. The only thing I would encourage you is if your code's not working and you're using a marked set, comment out the marked set because the marked set's not necessary for correctness and it probably will just, and it actually usually doesn't make that much of a difference with speed. Okay, so that's it for approach 2. Now, I should mention that there is an approach 3 for those of you who don't like the idea of having multiple copies of w on the fringe. And in that case, you could try approach 3 But I think on a practical basis, it's not going to make your code that much faster, but you could try it out if you want. That'll be in the next video.